Hello, so today I'm looking at M3 International A-Level May 2016. This is question 4. And so I have a particle of mass m is fired vertically upwards from a point on the surface of the Earth and initially moves in a straight line directly away from the centre of the Earth. When p, the particle, is at a distance x from the centre of the Earth, the gravitational force exerted by the Earth on p is directed towards the centre of the Earth and has a magnitude which is inversely proportional to x squared. At the surface of the Earth, the acceleration due to gravity is g. The Earth is modelled as a fixed sphere of radius r. So first of all, I'm asked to show that the magnitude of the gravitational force acting on p is mgr squared over x squared. So they told me that the force was inversely proportional to x squared, so the force will therefore equal k over x squared, and I need to work out k. So on the surface of the Earth, I know that that force is mg, so mg is equal to k over x squared, but on the surface of the Earth, x equals r, so therefore I end up with this expression here, this equation, mg equals k over r squared. And rearranging, I get that the k is mg r squared. Therefore, the force is mg r squared over x squared as required. And that's the first two marks. Then I'm told that the particle was fired with an initial speed u, and the greatest height above the surface of the Earth reached by p is this. And remember, whenever you have a greatest height problem, it means that the velocity is 0. So given that air resistance can be ignored, find u in terms of g and r. Okay, so what can I say about this particle? I know that I have the surface of the Earth, there's r, everything is measured from the centre of the Earth, so there's x. I know that when it's at this random position, a distance of x from the centre of the Earth, I've got the force towards the centre of the Earth of this, mg r squared over x squared. I know that the acceleration is measured, because x is measured in this direction, x double dot is measured in this direction. And I can therefore write down, using Newton's second law, that the forces away from the centre of the Earth, which is nothing, minus the force towards the centre of the Earth, equals the mass times the acceleration. Now for the acceleration, I could use dv by dt, or I could use v dv by dx. And in this case, as they've given me this force in terms of x, it's a much better idea to use this. So I have v dv by dx. So I can see that I have m on both sides, so I can divide both sides by m. And now I can separate and integrate. So on the right hand side I have the integral of v integrated with respect to v. On the left hand side I will have negative g r squared integral of x to the negative 2 dx. And I can do an indefinite integral, or because I know kind of my initial conditions, then I can put in some values here to make this a definite integral. So let's just look at what those were. It said the particle was fired with initial speed u, and the greatest height, so I know the final speed is v. So the initial speed is u, and the final speed is 0, because at the greatest height the particle will have stopped moving. As for the distance, well, I know the particle was fired from the surface of the Earth. Here we are. It was fired vertically upwards from a point on the surface of the Earth. So I know that initially the value of x must be r, because the particle is here. And then I was told halfway through the question here, the greatest height above the surface of the Earth is r over 20. So I just need to be a little bit careful here, because this r over 20 is the distance from the center of the Earth, from the surface of the Earth to where the particle is, whereas I need to give a value of x which goes from the center of the Earth to where the particle is. So I just need to do x plus, r plus r over 20 to give me the upper limit of this integral here. So this would be 20r over 20 plus 1r over 20 makes 21r over 20 as the upper limit of my integral. So now I can do the integration. So on the left hand side I'll get negative gr squared. Here I get add 1 to the power, divide by new power to evaluate from r to 21r over 20. And on this side I end up with v squared over 2 to be evaluated from u up to 0. So here I will begin by writing negative gr squared. Now I pop this into here, so I would get negative 1 over this, so 1 over 21r over 20 would give me 21r on the bottom and 20 on the top. Then I would subtract what I get when I put r into here, so negative 1 over r. Here I begin by putting 0 in, which is 0, and then I subtract what I get when I put u in. Okay, so now I can work out that I've got negatives on both sides, so I could just do that and multiplying both sides by negative 1. So here I've got 1 over r, which is positive, take away 20 over 21r. Now if I multiply the top and bottom of this fraction by 21, that will make it a bit easier. So I've got 21 over 21r minus 20 over 21r. So that leaves me with 1 over 21r. So I end up with gr squared over 21r. I noticed that I could have cancelled an r here even, but if not I'll just do it here. And here I've got u squared over 2, so I'll double both sides, and so the 2 ends up here. They wanted u in terms of g and r, so final line, u will be 2gr over 21 square rooted. Okay, and this gives you the initial speed u, which is the speed with which it was fired. Okay, so that part of the question is worth 7 marks. I hope you found that solution helpful. Do click like if you like this video, and good luck with your studies.